Rolling here. All right. So right now we are still working through lecture set 2 of the Stat 252 material. So our focus has been on hypothesis testing for a single population mean. We have talked about, it's been on hypothesis testing for a single population mean and confidence interval construction for a single population mean. So we have looked at how to construct intervals based off of the standard normal distribution and how to construct intervals based off of the student's t-distribution. And right now, we are in the middle of refreshing our understanding of how to conduct hypothesis tests when sigma is known and when sigma is unknown. So when sigma is known, and we've looked at 2 examples of this already, our test statistic will be Z, or will be standard normal distributed, and our method for finding the critical values and the p-values will utilize the standard normal table. When the population standard deviation is unknown, we have to use the student's t-distribution to complete the hypothesis test. So this means that our test statistic will now be student t-distributed, and our technique for finding the critical value and the p-value will utilize the student t table. So in exercise 2 on slide 35, we're going to work through an illustration of conducting a 1 sample hypothesis test when the population standard deviation is unknown. All right, so in this illustration, we have a manufacturer produces bolts that are supposed to have a weight of 2.50 grams. A simple random sample of 20 bolts, yielded X bar equals 2.53 grams and little s equals 0.04 grams. Is there any evidence that the population mean is different from 2.50 grams at alpha equals 0.01? So we'll just start off like we did before and write down what we know. So we have mu is equal to 2.50. We have X bar is equal to 2.53. We have little s is equal to 0.04. And we have little n is equal to 20. So in this problem, it's very clear that we do not have any population information. We are only working with sample information. So our hypothesis test is going to be done entirely using the student's t distribution. Okay, so the first thing, we'll just do a quick assumption check here. So we have 1 and we have 2. Okay, so the first assumption is SRS, which is fine. We can see from the description that this is okay. And in terms of normality, it's not clear. So we don't have any information that would suggest that bolt weight is normally distributed. And our sample size is only 20, which means that the central limit theorem is not going to apply. Notice, or in this exercise, we actually have, after the test, a discussion of the validity. So we'll come back to talk about this normality assumption in a bit. But when we conclude the test, we'll make a note about normality, and we will then discuss one of the ways in which we could try and verify this. Okay, so now we'll start working through the actual test. All right, so on step 1, we will state our hypotheses. So the question asks, is there evidence that the population mean weight is different from 2.50? So in this situation, we will have a 2-tailed test. Right. So notice here we have the does not equal sign. which corresponds to being different from. So we're reflecting the question of interest through the alternative hypothesis, which is always the case when we're conducting our hypothesis tests. On step 2, we state our significance level, which is alpha 0.01. And then on step 3, we compute our test statistics. So we're going to have T is X bar minus mu. Well, I guess we can call this mu 0 divided by S over the square root of n. So this will be 2.53 minus 2.5 divided by 0.04 over the square root of 20. And that should give us roughly 3.354. Okay, now on step 4, we can take either the critical value or the p-value approach. So if we take the critical value approach, we'll have the following. So we'll start by sketching out our student T curve. Okay, so that'll look something like this. Right, so this curve is centered at 0, just like the standard normal curve. We're performing a two-tailed test or a two-sided test. So we will have a critical value in the upper tail and we will have a critical value in the lower tail. So these two red shaded areas here, these represent the rejection region for this particular test. So in the upper region, we're going to have a t value on alpha over 2 and n minus 1. So this is going to be a t value on 0.005 and 19. And then in the lower tail, we will just have the negative of this. So this will be a t on 0.005 and 19. Okay. So as a reminder, we're splitting alpha equally into each tail because it's a two-sided test. Yeah, so the alpha is 0.01, but because there are two tails, we're splitting that area equally. So we would have a 0.01 total area, which corresponds to 0.005 in the upper tail and 0.005 in the lower tail. Hence the alpha over 2. Okay, cool. All right, now to find the critical value, we go to the student T table. Finding critical values with the student T table is typically probably the easier practice in terms of finding critical values or p-values across both types of tests. In this case, we're simply matching the significance level to the degree of freedom. So we have T subscript 0.005. We have 19 degrees of freedom. So that gives us a critical value of 2.861. So we have 2.861 here, and then we'll have negative 2.861 in the lower tail. The test statistic is positive 3.354. So we'll mark that down about here. So this is T equals 3.354. So we can see that based off the critical value approach, we are inside the rejection region. So then on the fifth step, we can reject the null hypothesis. Right? Okay, so this is the critical value approach to the problem. We could also take the p-value approach. Now, just before I flip, if anyone is writing this down, does anyone have any questions about what we've done so far? Okay, so if we take the p-value approach, we'll start by sketching our t-curve. Okay, centered at 0. Okay, now with the p-value approach, we're going to mark down the value of the test statistic in both the upper and lower tail. Because again, this is a two-tailed test, so we have to consider each side of 0. So let's say our test statistic is right about here. And then in the lower tail, let's mark it roughly right about here. So these green shaded regions underneath the curve, those represent the region of the p-value. So in this situation, we can write that the p-value is the probability t is less than negative 3.354 plus the probability t is greater than 3.354. Now, since the curve is symmetric, so and both areas are therefore the same size, this is just 2 times the probability t is greater than 3.354. All right, now to find this probability, we go back to the student t-table. To find probabilities using the t-table, we first identify our degrees of freedom. So in this case, we again have 19 degrees of freedom. Now what we do is we work our way across the line to determine where our test statistic will be located. So the first value on line 19 is 1.328. Our test statistic is bigger than 1.328, so we move to the next value. The next value is 1.729. Our test statistic is greater than 1.729, so we move to the next value. The next value is 2.093. The test statistic is again greater than this, so we move to the next value. The next value is 2.539. The test statistic is again greater than this, so we move to the next value. The next value is 2.861. Our test statistic is greater than this, so we can say that t is going to be on the right side of 2.861. So somewhere, well, it's to the right of this value. Okay, now the way that the t-table works, each of these little subscripted areas here represent the area to the right of the listed value. So for example, to the right of 1.328 is 0.1 of the area underneath the curve. So if we go back to our line, line 19, if we consider the value 2.861, okay, what the t-table is telling us is that the probability that t is bigger than 2.861 is equal to 0.005. Now, because our test statistic is larger than 2.861, that means that the area to the right of 3.354, so the area to the right of our test statistic, must be smaller than 0.005. So what we can say is that since the probability that t is greater than 3.354 must be less than 0.005 based off of the student t-table, then the p-value is less than 2 times 0.005. So the p-value is less than 0.01. Okay. Any questions? All right, so when we're finding area using the student t-table, we start by isolating our degree of freedom. So we have 19 degrees of freedom. Each value in the t-table represents a value with the subscripted area at the top of the column to its right. All right, so for example, let's consider this value here. What the t-table is telling us is the probability t is greater than 1.328 is equal to 0.1. If we consider the 2.861, okay. So when, sorry, this is all when the degrees of freedom is 19. Obviously it changes, right? So the probability that t is greater than 2.861 is equal to 0.005. All right, does that make sense? Okay, so our test statistic is 3.354. 3.354 is bigger than 2.861. Therefore, if the area to the right, or if the probability that a value greater than 2.861 is 0.005, then the probability that the area to the right, or the probability of observing a t-value larger than 3.354 must be smaller than 0.005. Okay, basically, because the test statistic is larger than the largest listed value, the area to its right must be smaller than the smallest listed area. So that's why we are using 0.005. Does that help? All right. So each of these tails here are going to be an area that is less than 0.005. Right? So since each tail has an area smaller than 0.005, the total p-value is just the sum of the two tails. So all we can say is that the total p-value must be less than 0.01, which is what you get when you add 0.005 to 0.005. Any other questions? All right, so we can see that regardless of which approach we take, we're going to end up with the same conclusion. So in both cases, we are going to reject H0. If we consider the critical value, we can say that t equals 3.354 is in rejection region. And if we consider the p-value, we can say the p-value is less than alpha. And as always, the conclusions from each test will always, they always agree. So if we have rejection from the critical value, we will have rejection from the p-value. So you don't have to do both. I'm just illustrating both the critical value approach and the p-value approach, so you have examples of both. But unless you are told which one to calculate, you can choose the approach that you would like to take. And this question or this illustration would be an example of how to conduct a one sample student t-test, which is the third last question on assignment 2. So at this point, you can complete all of assignment 2 except for, we haven't just, well, I mean, if you're reviewing your old notes, you can complete all of it because it's still all review. But we haven't covered the multiple choice question yet. And we haven't covered the last 2 questions yet. Yeah, so to clarify to Danielle's point, you should be comfortable with both, because at some point you will be asked to compute a p-value and you will be asked to compute a critical value separately. But if it does not specify, then you can choose either approach. Okay, now for step 6, we have to conclude our test. So the first thing we should do is write out our condition based off of the fact that we did not, we could not verify normality. So we would have here, if the normality assumption can be verified, then the data provide sufficient evidence to suggest that the population mean bolt weight is different from 2.50 grams at the 1% significance level. Okay, so step 6, effectively inside of this statement, we have our standard conclusion to a hypothesis test. So after the condition, I just have the data provides sufficient evidence to suggest that the population mean bolt weight is different from 2.50. Now, in this situation, I've stated the significance level at the end of the statement. It doesn't really matter where you put it as long as it makes sense in the context of the sentence and it's included. And I've started off with the condition because we could not verify normality. So if we cannot verify the normality assumption, this result could be meaningless. So this conclusion is conditioned on us being able to verify that. Okay, now let's briefly chat about verifying the normality assumption. Okay, so in general, there are 2 different ways that I would think to do this right off the start. Okay, the first way, which would be the more common way, especially at this level, would be construct a normal probability plot. So we've talked about normal probability plots a bit. Again, the idea here is we are going to plot each observation. I think I mentioned them, sorry, and then in lab I talked about them in more detail. So I have an illustration of the normal probability plot coming up momentarily, but just as a quick recap, essentially what it is a scatter plot where on one axis you have values from the standard normal distribution, and on the other axis you have your observed values or a transformation of the observed value, like a standardized value. If the values form a straight line relationship, that's evidence of normality. So one way that we can verify normality is through the normal probability plot. And when we use the normal probability plot, which we won't construct by hand, but you will construct in SPSS, all you are doing is looking for a straight line relationship between between the points that are on that grid. So those would be the values of the standard normal distribution versus your observed data. Now, the other way that we can do this is through the Shapiro-Wilks test. Now, this isn't something that we're going to talk about a lot in Stat 252, but the Shapiro-Wilks test is a formal hypothesis test for normality. So the Shapiro-Wilks test has null hypothesis. The data is, or the variable of interest is normal, versus the alternative that the variable of interest is not normal. There are other versions of this test. So there are more than one hypothesis test for normality, but this tends to be the most common one. And this test would give you, for example, a p-value that you could use to determine if there is statistical evidence that the data is normal versus being non-normal. Most often in this class, we will focus on the normal probability plot, but I wanted to bring to your attention that there are formal hypothesis tests for normality. All right, let's look at one more example of conducting a t-test. So here is an illustration of a normal probability plot, and I will talk about what we are looking at in a moment as soon as I work through the problem description. So in this problem, it says, according to Communications Industry Forecast and Report, the average person watched 4.55 hours of television per day in 2005. In 2015, the average amount of time spent watching TV in a simple random sample of size 20 was 4.76, with a standard deviation of 2.297. At the 10% significance level, do the data provide sufficient evidence to conclude the amount of television watched per day in 2015 is different from that reported in 2005? Okay, so let's start off as we usually do. Let's just make some notes here. So we have mu is 4.55. We have X bar is 4.76. We have little s is 2.297, and we have a sample size of 20. Okay, so first off, our normality assumption, or the simple random sample assumption, based off the problem description, this is fine because we have written that it was an SRS. Normality. Okay, so when we are working with a QQ plot, we have, in this case, standard normal values on the x-axis. All right. And then here we have representation of observed data. Now, when I say representation of observed data, I just mean that some QQ plots or normal probability plots typically apply some kind of transformation to the observed data, usually in the form of a standardization. So we talked about this idea in the previous lecture set where we had y minus y bar over SI. So that's just a standardization of the observed values. But you can also create normal probability plots where you just plot the observed value against the quantiles of the normal distribution. And this is how we usually teach it at the first year level. Regardless of what we have plotted, the way that we use the graph is exactly the same. So what we are looking for here is evidence of a linear relationship. So you can see that the normal probability plot has a straight line going through the data. That straight line is our reference. And what we are trying to do is determine if the observations follow that straight line pattern. Now, it doesn't have to be an exact fit, but obviously we would like the points to be as close to that straight line as possible, because the closer they are to the line, the more evidence we would have of a linear relationship. Now, in this particular situation, I think that when we look at the line, we can see a little deviation here, and we can see a slight deviation here. All right, so this is what we would call kind of a lower S shape, but it's not that symmetric. So you can see that the deviation in the top part is a little bit more extreme than the deviation in the lower part of the graph. Typically, when we observe this kind of S shape like this, that implies that the data have heavier tails. So it seems like in this case, we have a slight outlier probably in the upper tail. So this point here might be an outlier. So potential outlier. And that is what that observation alone really seems to encapsulate this deviation. So in this situation, we're probably okay to proceed and say that normality is, we have evidence of normality, but we should investigate this outlying point. However, someone that's more strict might say that this is emitting an S shape, which is evidence of a student T distribution rather than a standard normal distribution. Okay. So there is subjectivity in using the normal probability plots to verify normality, right? A very strict statistician might say that this is not close enough and that these deviations do not warrant normality. Whereas in other cases, you might have someone that says, investigate that point, but it looks like we're okay to proceed. Hence, again, the idea of using formal hypothesis tests for normality, because that removes some of the subjectivity from the problem. So just for the purposes of the illustration, let's say evidence of normality from the normal probability plot should investigate flagged points. And then just on the topic of this flagged observation, let's say that this point is in fact a value that we have collected, but there was a measurement error attached to it. So something like the person that sampled the data introduced some kind of error, then that point you could argue might have to be removed. And if you take that point out, we now have a sample size of 19, but it does look like the observations fall very close to the line. So you can kind of see how you can make arguments either way. Now, the other thing is what we're starting to set up here is this assumption of normality is a very fragile assumption in a lot of cases. So what do we do when we really can't say it's normal or we're not comfortable with the normality assumption? Well, the answer to that is we start to explore what are called non-parametric tests, and that forms the middle part of Stat 252. So we will continue to see examples of ways that we'll continue to see examples of where the normality assumption might be, difficult to validate, but we do have a whole other set of tests that we can utilize when we can't assume normality for the variable. But right now we're just reviewing our standard set of tests. All right, so let's assume our assumptions are intact. We have our data written down. We have our summary statistics written down, no population information. So we're going to be using a t-test here. All right, so now we can start to work through the steps of our t-test. So we have H0 mu equals 4.55. And we are again conducting a two-tailed test. All right. On step 2, we have alpha 0.1. All right, and then on step 3, we have t equals x bar minus mu 0 divided by s over the square root of n. So we have here 4.76 minus 4.55 divided by 2.296 over the square root of 20. 2.296, 2.297. Oh. Okay, and that's going to give us a test statistic of 0.409. All right, so if we take our critical value approach, we are again going to start by sketching our student t curve here, centered at 0. All right, so we're going to have a t value in each tail. So that's again t alpha over 2 n minus 1. So t 0.05 comma 19. And then in the lower tail, we're going to have negative t 0.05 comma 19. All right, if we go back to part 1 or to our student t table, we're simply matching 0.05 to 19 in this case. So our critical value for this test is 1.729. All right, so we have negative 1.729 and we have positive 1.729. And then we can see that the test statistic in this case is somewhere in between the two. So probably right about here. Right, so this is t equals 0.409. All right, so based off the critical value approach, we are not inside the rejection region. And then based off of the, and then we can also consider the p-value approach. All right, so if we take the p-value approach, okay, then we have the following. I'll just leave it here for now. Okay, so we're going to mark down where the test statistic is located in this case. So you can see that we have t equals 0.409. We also have to consider the negative because it's a two-tailed test. So the test statistic area will be this green shaded part here. And then our formal definition of the p-value is going to be 2 times the probability that t exceeds 0.409, right? Again, is the sum of those two areas. The areas are symmetric, so it's just 2 times the probability of being larger than the test statistic. Okay, so if we go to our student t table, we isolate our degrees of freedom, which is 19. Now we can see that our test statistic is actually to the left of the smallest listed value. Now, as we established before, what the t-table is telling us is that the probability that a student t variable, so the probability that t equals 1.328 is equal to 0.1. Okay, so the probability of observing a test statistic of 1.328 is 0.1. Since our test statistic is smaller than the smallest listed value on the line, the probability of being greater than our test statistic must be larger than 0.1. So what we can say in this case is, since the probability t exceeds 0.409 is greater than 0.1, the p-value must be greater than 2 times 0.1. So the p-value is greater than 0.2. So the t-table is telling us basically that this area is bigger than 0.1 and this area is bigger than 0.1. Any questions about that derivation? Well, calculation, table usage, whatever you want to call it. All right. Okay, so based off of either approach, we can see that we will not reject the null. So if we wanted to break this down, we could say test stat not in rejection region, or we could say the p-value is greater than alpha. All right, and then we can say at the 10% significance level, the data do not provide sufficient evidence that the population mean amount of TV watched in 2015 is different from 4.55 hours. All right. Okay, so does anyone have any questions about the one sample hypothesis tests or intervals? All right. Okay, so with the time that's remaining, I'll set up the next lecture set. So that brings us to the end of lecture set number 2, which is focused on single sample inference. Our next lecture set is lecture set number 3, which is focused on 2 sample inference. In this lecture set, we are going to review the 2 t-tests for conducting inference about 2 population means. So we are going to look at, or sorry, and we're also going to review the associated confidence intervals. It's all one package, right? So the first thing that we're going to do is review the distribution of the sampling mean difference. Then we will talk about a confidence interval for the difference between two population means when the samples are independent of one another. And then we will talk about a confidence interval and hypothesis test for two population means when the samples are considered dependent or paired. So when they admit what is called a paired structure. So we're focusing on two different sets of tests for the same quantity, but we differentiate between the test based off of data structure. Now, all of these hypothesis tests and intervals, as you will see, utilize, again, the student t-table. So once we compute the test statistic, everything is essentially the same as it was before. The only real differences between this testing procedure and what we have just finished reviewing in lecture set 2 is, well, from a systematic point of view, will be on step 3 and step 1 of our 6-step procedure. And then for the interval on step 2, because the formula will be slightly different to accommodate the two samples of information. All right, so what is two-sample inference? Two-sample inference refers to methods that we use to make statements about the population mean difference. So our focus in this unit is on either answering a question about mu1 minus mu2 or building a confidence interval for mu1 minus mu2. So when we are interested in conducting two-sample inference, we do it by comparing the difference of the two population means that we are studying. In lecture set 1, we defined the parameters of the sampling distribution of X bar. So we said the mean of all sample means is equal to mu, and the standard deviation of all sample means is equal to sigma over the square root of n. We then went on to say that these two parameters will parameterize a normal distribution if the population is normal, or we collect enough information that the central limit theorem would apply. It turned out that our inferential procedures were actually based off of these parameters. So for example, for the Z hypothesis test, we had Z equals X bar minus mu over sigma divided by the square root of n, right? So that is X bar being standardized by its parameters of its sampling distribution. So if we want to conduct two-sample inference, we need to establish the parameters of the sampling distribution of the sample mean difference. Okay, so if we consider slide 4, what we are showing here is that if the variances from the two populations we are studying can be considered different, then the sampling distribution of X bar 1 minus X bar 2 has a mean of mu1 minus mu2 and a standard deviation that's equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. You can see that this is very similar to what we saw in the one sample case. In the case of the means, we are literally just subtracting the two population means. In the case of the standard deviation, we are just adding the sampling distributions of the sample mean from each population together. This is because variance squares constants, not something we have to worry about, but hopefully you can see the similarities between these formulas and the one sample formulas. Now, just like in the one sample case, if we sample from two normal populations, then the distribution of our difference will also be normal. If we sample from two populations that are not normal, we can apply the central limit theorem to each sample mean as long as we collect more than 30 observations. So our two sample approaches are very direct extensions of our one sample approaches. Okay, so on Wednesday, we will start to work through examples of applying the two sample inferential techniques. And as always, if you guys have any questions, please let me know. And otherwise, have a good couple of days, and I'll talk to you on Wednesday afternoon.